Good afternoon, dear students.
Good afternoon, ma'am.
We are discussing about test bench of different VHDL code. Okay, so which is written for the different circuits. So for that, how to test that code that we are looking for. Okay, and we have written test benches for a different circuitry like a half adder, then full adder, then encoder. Okay, so in
Comparator.
continue. Yes, comparator also. So for that also we have written the test bench. Okay. Now in continuation with that, today we are going to discuss about some more different circuits like decoder, multiplexer, demultiplexer, and then after that we are going to discuss about D-flip-flop. Okay. So let us start with the first circuit, that is a decoder. Now tell me what is mean by decoder.
Decoder is a combinational circuit which used to decode the encoded data.
Which yes, it is a combinational circuit which is used to decode encoded data. That means it is actually the circuit which gives us a output which is in terms of which is a decoded output which the circuit has encoded input. Okay, so here uh, we have 3s to 8 decoder. That means for any decoder circuitry we have if it has n number of inputs, then it will give us 2 raised to n number of outputs. Okay, so that means if it has 3 inputs, then outputs for that circuitry will be 2 raised to 3. That means it is a 8. Okay, so we are looking for 3s to 8 decoder, and this is the VHDL code for that circuitry. Okay, so here as we know that whenever we are writing VHDL code for any circuitry, we first declare library, after that entity declaration, and then architecture declaration. So the first part, that is a library declaration, which has library, that is a IEEE library that we have uh, included. Then package that is added, that is IEEE dot std underscore logic underscore 1164, and all the functions of that package that are added here. So that dot all. Okay. So that means the first part that is covered, that is a library declaration. And after that, we entity declaration with port definitions or port declaration. Okay. So here the name that we have given for this entity, that is a decoder. So entity decoder is, and in this we have three inputs. Okay, so instead of studying all these three input differently, we have considered it as a vector. Okay, so that means now we are considering a bus, and then input, that is in type, that means direction of that port, that is a in, and which is a std underscore logic underscore vector. Okay, as I said that we are considering here a bus. So the range for this is a 2 down to 0. That means it is a 3-bit input. Okay, and now again a output is a 8-bit output. So output, that is the out, which is again std logic underscore vector, which is 7 down to 0. That means it is a 8-bit output. And then as we have declared all the ports here, so end of the decoder. Okay, now if you would have selected a single bit input, then you have to write 3 inputs here and add 8 outputs. Okay, so that you need to write, but here I just have considered a vector. So in a single line or single statement, we have covered all the input ports as well as all the output ports. So this is the entity declaration part of this VHDL code. Okay. After that, now, so once you complete port definitions, complete um, or end this entity with a end decoder. Okay, as the name for this entity, that is a decoder. So end decoder. Then after that, we need to declare architecture of this entity. So architecture behavioral, let us name for this architecture uh, that we will give as a behavioral. So architecture behavioral of decoder is okay. And now we are considering each of these 8 outputs. Okay, so output 0. Okay, so that means 0th output, LSB output of this vector, that will be assigned to not okay. Now if you have the truth table for this decoder, then you will find get boolean expression for the output. So 0th output, that is nothing but if x, y and z, these are the 3 inputs, then it is a x bar, y bar, z bar. That means it is a ending of not of x, not of y and not of z. Okay, so here we have considered the input name given for these inputs, that is a input. Okay, and it is a vector. So it will have 3 bits like input 2, input 1 and input 0. Okay, so output 0, that is not nothing but not of input 2 and not of input 1 and not of input 0. Okay, and that is why this boolean expression that we have written here. So output 0, that is assigned to not input 2 and not input 1 and not output 0. Okay. Similarly, this is the expression for output 1, that is a not of input 2 and not of sorry not of input 1 and input 0. Okay, so in this way you will find all the expressions for these outputs. Okay, so check these outputs from the truth table. Okay, so here as we have 3s to 8 decoder, that means depending on the input combinations, each any one of the output that will be high, others output that will be at a logic 0. So we get this type of expressions for each of the output. Okay, so in the earlier sessions we have discussed about this VHDL code. Okay, so without wasting much time on discussing on this, so let us go to the test bench of this code. Okay, so here we have ended this architecture, and then let us discuss about test bench for 3s to 8 decoder. Okay, now as we are going to associate this test bench with the VHDL code of the decoder that we have already written, and the entity name that we have given for this is a decoder. Okay, so now let us discuss about the test bench. Okay, so here IEEE library, that is we need to include in this test bench also, because this test bench, that is again a VHDL code. So library declaration, that will be the first part, after that entity. And as I have earlier stated that here we are instantiating a component. Okay, so decoder component that we are taking in this or connecting in this test bench. So there is no need to declare ports in this, but entity that we have written for this, then after that declare architecture declaration. Okay, so the signals that we have used in this, that is the input and output. Okay, so this will be treated in a test bench, input and output ports of the decoder VHDL code. So that will be treated as a signal in a test bench. And so here uh, signal input, that is a std underscore logic underscore vector, which is of 2 down to 0, that means it is a 3 bit. So all the bits in this that we are assigning to 0. Okay. At the same time here for the output also we are assigning all the bits in this vector to 0, because what we want actually in this circuitry, what only one output should be at a high logic level, others should be at a zero logic level, and so to ensure this that others are going remaining at a zero logic level, we are initially making this output signal that is 0. Okay. Then after that we are instantiating a that component decoder. Okay. So now instead of going for the calling component differently, here what we have done, we have taken entity from that is a work dot decoder. Okay. And then we have mapped port of all this entity, that is a port map input and output. So whatever ports that are available in the decoder, that will be mapped to the ports of this unit under test. Okay. जो काही युनिट अंडर टेस्ट आपण करतोय त्याचे जे पोर्ट्स आहेत आणि डिकोडरचे पोर्ट्स आहेत ते मॅप केले जातील. ओके. सो इन्स्टेड ऑफ डायरेक्ट गोइंग फॉर द कंपोनंट there, we have just directly taken this. Okay. After that now there will be a stimulus process. So the process name that is given as a TB and then begin. Okay. Now whenever we are writing a test bench, that means here what we are doing, we are just stating what will be the input condition, and depending on that after simulation we will get what will be the output. So here uh, we have the first condition, that is the input, that we are assigning to 0 0 0. So now the first condition will be 0 0 0. Then after that we are going to wait for 2 nanoseconds. Okay. So as now here remember that this statement has to be used after uh, any input combination. Okay. And before changing it to the another input combination, because there are certain delays that will be present in this circuitry, and so to make sure that there is no any overlapping, so we have to take introduce certain delays there. Okay. So wait for 2 nanoseconds, and after that input that is has been changed to 0 0 1. Okay. So there are certain different combinations that I have used for this input. Okay. And then wait, and then end of this process TB and end of the architecture. Okay. So here this is the test bench for 3s to 8 decoder. And then when we are simulating this, we will get this type of result. So whenever input combination that is a 0 0 0, that time you will get that output 0 is at high level. Uh, 0 MSB, sorry, LSB will be at a high logic level, and all others that will be at a 0 logic level. Okay. So similarly you can check it for the another combinations, and you will find that in at every instance only one output, one bit is at a high logic level and others are at a 0 logic level. Okay. So check for each of the combinations. प्रत्येक कॉम्बिनेशनला चेक करा की इथे आता 0 आहे, तर 0 ला काय व्हायला पाहिजे, आपलं आउटपुट 0 हे 0 यायला पाहिजे. ओके. देन 1 असेल तर D1 म्हणजे आउटपुट 1 बिट हे हाय असायला पाहिजे आणि बाकीचे सगळे 0 असायला पाहिजे. 2 ला आउटपुट 2 हाय असायला पाहिजे, बाकीचे 0. 3 ला आउटपुट 3 हाय असायला पाहिजे, बाकीचे 0. So in that way check it for each of this conditions, and then you will find that once you complete this, you will find that whatever result that we are getting, that is a correct. That means whatever code that we have written, that is a correct code. Okay. So this is about the 3s to 8 decoder. Okay. Anyone has doubt about this circuit, this code?
No, ma'am.
Others reply. Sandhya, doubt? Any doubt?
No, ma'am.
Okay, so let us proceed. Okay, now again, here whenever we are writing a test bench, that time you just need to specify what will be the input, and depending on that you are checking the output. That means actually you are giving a test vector and as a input to that circuitry, and from that you are checking the output. Okay. So let us move to the another circuitry, that is a 4:1 multiplexer. So what is mean by multiplexer?
It is also a combinational circuit which convert many into one.
So multiplexer, that is a combinational circuit which converts many into one depending on the select input. Okay, so there are certain select inputs and input available at, or the logic available at that select inputs. Uh, it is decided that which input should be present at the output. Okay, so here we are considering 4 as to 1 multiplexer. Now if there are 2 raised to n number of inputs that are present, then that circuit multiplexer requires n number of select lines. Okay, so that means if it is a 4 input multiplexer, then it requires 2 select lines. Okay, so here we have 2 select lines, 4 inputs and 1 output. Okay, so the VHDL code for this circuit will be uh, the library declaration, that is the first part, and after that in a entity mux is there are 6 input ports, that is the S1, S0, then A, B, C and D, and then in these are the input, and Z, that is the output. After that it is there is the end of this entity, and then in a architecture, here name for this architecture given, that is a data of this entity mux, and as we are going to use a behavioral type of modeling, so we need to declare process here, because whatever statements that we are having, we want to execute these statements sequentially, and that is why we need to define process. So the process which has the sensitivity elements, that is the S1, S0, A, B, C and D. Okay, these are the input pins, and S1 and S0, these are the select lines. Okay, so as all these are going to vary at with respect to time, depending on the how we are applying input. So these will be the sensitivity parameters. Then beginning of this process, so we start with a begin. Now if S0 is 0 and S1 is 0, then Z will be assigned to the value whatever is
A.
having A. Okay. Then for S0 is 1 and S1 was 0, then Z will be equal to B. For S00 and S11, then Z will be assigned to C and SZ will be assigned to D. Okay, so this is the VHDL code for this 4:1 multiplexer. Okay, and so for this test bench will be, now the first part, that is a library declaration, that is library IEEE, then use adding package to this, that is std underscore logic underscore 1164 dot all, so that package is added, and then entity that for this test bench. Okay, so the name for this entity given as a mux4 underscore tb. Here we are not declaring any ports. Okay, so end of this mux 4 underscore tb. Then architecture mux4 underscore tb of, okay. So here now you can see that the same name is given for the mux as well as architecture as well as entity. Okay, so that is also you can do in a PHDL code. Okay, so is now here we are called in architecture we are declaring ports for the, or we are declaring the components. Okay, so component mux4, that is port, okay, for this component that are A, B, C, D, S0, S1, and out, these are the input ports, and Y, that is the output port. Then end of this component. Okay, now these ports, okay, so that will have certain signal, and this whenever we are having this inputs at the test bench, so this as these are varying, so we are considering it as a signal. So signal, now initial value for these signals, input signals, that we are going to change. Okay, so not, we are not resetting these inputs. So signal A, that is assigned with the value 1. Okay, signal B, that is 0, signal C, that is a 1, and signal D, that is a 0. Only signal S0 and S1, these we are keeping as a 0 0, and then signal Y, which is the output, so that we are not assigning any value to this. Okay, but here you can see that we have already assigned these values to A, B, C, D, that is a 1 0 1 0. Okay, and then in a stimulus process, we now just uh, changing values of S0 and S1. Okay, so that means we are giving different logic levels at S0 and S1, but we have fixed the values for A, B, C, D, that is a 1 0 1 0. So S0 will be now assigned to 0, and S1, that is assigned to 0. And then we are going to wait for 50 nanoseconds. Okay. Now again I am telling that you can change this time period. Okay. So the delay that you decide to what you want. Okay. So now we have kept it as a 50 nanoseconds. Now once uh, you have this input, okay, you can change for the another combination, that is S0 0 and S11, or you can change it to S01 and S10, and last combination for this is a S01 and S11. Okay, so now here at the last after last input combination, you have to have the statement that is wait. Okay, end of this process, and then end of the architecture. Okay, so this is the test bench code for this so VHDL code for multiplexer. Okay, and then when you exit that program, that time you will find that we have already initialized values for D0, D1, D2, and D3. Okay, or actually A, B, C, D. We have taken these values as a or variable names as A, B, C, D. So this A, that is a 1, B, that is 0, C 1 and 0. Okay, and after that S0 and S1, that we are changing in a process. Okay, so here after 50 nanoseconds, each combination, that is a, or each input, that is changing. So here you can see that at a waveform. Initially this A, B, C, D, that is going to remain as a constant, that is a 1 0 1 0. Okay, only initially we have the combination for S0 and S1 as a 0 0, and at that time whatever is the, I, wait a minute. Yes, Y will be here 1 0 1 0, the ABCD, and S0 is 0, S1 is 0. So here y is equal to, in that condition, equal to A. So that means here A value is 1. So y is equal to 1. Okay. Then for S0 is equal to 0 and S1 is equal to 1, y is equal to b, and b has the value that is a 0. So here you will find that for the output it is a at 0 logic level. Then for 1 0 combination of S0 and S1, we have y is equal to c and y has the value that c has the value 1. So you will get y as output that is equal to 1. And for 1 1 combination, for the select lines we have output that is equal to D, which is having value that is a 0. So here you can find that this y that is equal to 0. Okay. So this is the output for this multiplexer circuitry. Okay. So now you can change this combinations. Okay. Whenever you are performing this circuitry in your laboratory, that time you can change this combination, and from that you can check whether you are getting same output or not. Okay? And from that you can test whether your design is correct or not. Okay. So this is about the multiplexer circuit. Okay. So if anyone has doubt, they may ask. So no doubt.
No doubt, ma'am.
Now you tell me. This is another circuit now that we are going to discuss, that is a demultiplexer. So first of all, tell me what is mean by demultiplexer.
It is a combinational circuit which convert one into many using select lines.
So write HDL code for demultiplexer. So 1 has to 4 demultiplexer, write VHDL code. I have displayed it. Okay, I have shared with my on my screen. So you can see this. Okay, and tell me how this will work. Okay, so what is first part?
Library declaration part.
Yes, library declaration part. Okay, with standard library, that is a or standard package, that is std underscore logic underscore 1164. I have added two more packages, that is a arithmetic package and unsigned number package. Okay, so that is a std underscore logic underscore arith dot all and std underscore logic underscore unsigned dot all. These two extra packages that are also added in this VHDL code. Okay. After that, there is a entity declaration. Now, what is entity declaration?
Input output declaration.
Input and output ports definition or declaration. So here we have given the name to the this entity, that is the entity demux underscore 14, and then we have the ports in this, that is a one input, then as for to get output. Okay, so here in this demultiplexer circuitry we have one input and four output. So depending on at which output input should be available to select or to decide that we need certain select inputs. Okay, and depending on how many outputs are there, there will be uh, that will decide the select lines. Okay, so here as we have 4 outputs, so it will require 2 select lines, because if there are 2 raised to n number of outputs, then we require n number of select lines. So here in this circuitry we will require 2 select lines. Okay, so now here in this code, now you can see that we have considered this select lines as a vector. Okay, so that means first, so that means this will be of a 2 bit. Okay, so s, that is the input port, which is a std underscore logic underscore vector, which is a 1 down to 0. That means it has 2 bit bus. Okay, so it is a 2 bit vector. Then y, that is the output port, which is a std underscore logic underscore vector. So again it is a 4 bit, so 3 range is 3 down to 0. Then end of the port declaration, so end of this entity, that is the end demux underscore 14. After that, architecture for this is, now here again we are writing a process in this architecture. So the sensitivity parameters, that is the I and S. Okay, so the select lines as well as the input, that is going to change. So if S is 0 0, then Y0 will be equal to 1. Or input, whatever is input available, logic level available at this input I, so that will be available at Y0. Else if S is 0 1, then Y1 will be equal to I. Then if S is equal to 1 0, then Y2 will be I, and else it Y3 will be I. So for this we have used these assignment operators. So if S is assigned to 0 0, then Y0 that will be assigned to I, and so on, that we have this code that we have written for the expressions that we have used in a architecture. Then end of this if, end of the process, and end of the behavior. So this is the VHDL code for demultiplexer. Now we want to write a test bench for this circuit. So here this is the test bench. So first part, that is the entity library declaration, after that entity declaration, and in a after that in a architecture, that is a TB of demux. TB is there we are calling a, or there we are declaring the component. Okay, so this component demux, that is which has the ports, that is I. Then again select lines S, which is a vector 1 down to 0. Y, that is the output port, which is again a vector, that is a 3 down to 0. And then end of this component. So these are the different uh, ports in a component. After that we have the signal declaration. So this signal I, that is of std underscore logic, then signal S, which is a vector, which is 1 down to 0, and signal Y, that is a std underscore logic underscore vector, that is a 3 down to 0. Now we have not initialized any value to this. Okay, so uh, whatever will be the logic levels that are available earlier, so that will be present here. Okay, so but we have not initialized, or we have not resetted that code here. So begin, that is a unit under test, that is a demux source. Here now we are mapping the port of this unit under test with the ports of the component. So I will be assigned to I, then S to S, and Y to Y. Okay, and after that now we are having a stimulus process. So now we are making I, that is equal to 1. Okay, so that means we are going to keep I, that is equal to 1, and then we are checking for the different combinations or different input logic level that are available at the select lines. So now we are making first select lines, that is 0 0. After that it is, we are going to make it as a 0 1, then 1 0 and 1 1. So all the combination for this select lines that we are having, and after each of this input combination we are going to have a delay of 20 nanoseconds. Okay, so you can see here that we have the statement that is wait for 20 nanoseconds, and then after that we are going to end the process and end of this architecture. So this is the test bench code for a demultiplexer, 1:4 demultiplexer. Okay, and when you are going to simulate this code, then at that time you will find that here value of I, that is continuously it equal to 1. Okay, now this select lines that are uh, first it is a 0 0, after that it is a 0 1 1 0 and 1 1. Okay, so this select line, it or this vector or this bus that is splitted here, so you can see that here S0, that is a 0, and S1, that is a 0 and 0, 1 0 1 uh, 0 1 and 1 1. So this combination that you can see for this select lines, and after that you can see that whenever select lines is 0 0, that time uh, this y0, that is 1. Okay, here you can see that it is a y0 that is at a high logic level and others are at a low logic level. Whenever there is a 0 1 combination, that time y1 is at high logic level and others are at a 0. For 1 0 combination, y2 is at high logic level and others are at 0. And for 1 1, y3 is at high logic level and others are at 0. So this is the output waveform for 1:4 demultiplexer. So you can check once again, you can check for the test bench code. So what we have done in this code, we have kept I value as equal to 1 for each of the time period. Okay, म्हणजे आय ची व्हॅल्यू आपण कंटिन्युअसली 1 ठेवली आणि आपण चेंज काय केलं, फक्त सिलेक्ट लाईनचं जे काही इनपुट आहे ते चेंज केलं आणि त्याच्यानंतर आपण फक्त वायच्या व्हॅल्यूज म्हणजे आउटपुटला प्रत्येक बिटला काय आउटपुट असेल ते व्हेरीफाय केलं. ओके, आणि ज्यावेळेस म्हणजे ॲज पर अवर ट्रूथ टेबल इफ वी आर गेटिंग द आउटपुट देन वी हॅव डिसाइडेड दॅट आर code is correct code. Okay, so that we can go for the manufacturing process. So this is the VH test bench code for 1:4 demultiplexer. Okay, everybody understood this? So now let us proceed with another circuit, that is a D-flip-flop. Okay, and here you can see that this is a VHDL code for D-flip-flop. Okay, here we are writing a code for how your D-flip-flop is behaving. Okay, so the first part, that is a library declaration. Then after that entity. So here there are input port, that is a D in, that is the input port. There is again one more input for the D flip flop, that is a clock. So that is again a input port. And also we have one reset signal as an input. So RST. that is the input port, which is of the type std underscore logic, and there is only one output port, that is a D out. Okay, so that is the output port, and that is of the std underscore logic. Okay, then end of the entity, and in a architecture behavioral of this entity, we have written a process. Okay, so in the process, there RST, that is a reset signal, then clock signal, and the input signal. These are the sensitivity elements. So that are in the bracket, that are we have mentioned in this bracket, and then beginning of this process. So now what we want, whenever reset signal is at high logic level, then D out should be equal to 0. That means that flip flop should be resetted. But if that condition is false, that means if reset is equal to 0, then we go for the another next statement, that is a rising edge of clock. If there is a rising edge of clock, then D out, that will be assigned to D. Okay, that means if reset is equal to 1, D out will be equal to 0. But if reset is not equal to 1, that means it is equal to 0. Then for the rising edge of clock, D out will be equal to D in. Okay, so this is the state. These are the statements that we have used to express this logic. Okay, so if RST is equal to 1, then D out, that we are assigning to 0. Else if rising edge of clock, then D out, that we are assigning to D in. End of if statement, end of the process, and end of the behavior. Okay, so this is the VHDL code for D flip flop, and after that we are going to write a test bench for this. Now here what we want, we are going for writing the test bench. So that means we are going to change the input signals. Okay, and from that we are going to check what will be the output. So this is the test bench for this VHDL code, which is associated with the earlier entity. So this library, first part declaration, that is a library declaration, then entity declaration, and after that architecture. In a architecture, we are declaring this component DFF, which we have VHDL code earlier that we have seen. Okay. Then here port of all these components, that is a D in, clock, RST, and D out. So all these ports that we have declared in this component, and after that end of this component. Then after what we are going to check, what will be the initial value on each of the signal. So there are signals that are D in, clock, RST, and D out. Okay, so we are assigning value 0 initially to the signal D in. Then for clock also we are assigning initial value as a 0, and for RST we are assigning it as a 1. Okay, so that means this flip flop will get resetted at the initial state. Okay, then signal D out, that is a, we are not assigning any value at a output signal. So then now we are taking here, now we require a clock signal. Okay, so we are taking a constant clock period of which has the time, that is of 10 nanosecond. Okay, so that means we are considering a clock signal which has the time period of 10 nanosecond. But initially here you can see that we have initially stated that the clock signal will have the value that is 0. Okay, then now after that we are going to check the or we are going to write the architecture for this unit under test. So here we are mapping all the ports of this unit with ports of the component. Okay, so we are mapping D in with the D in. So all the ports, that is the clock to with the clock of the component, then RST with RST reset of the component, and then D out, that is the output of the component. Okay, so whatever is the unit that we are designing here, all will have the same ports like the component. And after that, now here we need to write a clock process. Okay, so initially in earlier circuits we are not using clock signal. Okay, so this process is not needed, but here we need a clock signal. So for that we need to write a clock process. So initially clock will be this process, clock will be assigned to 0 value. Okay, initially. After that, wait for clock period divided by 2. Okay, now we have defined clock period that is of a 10 nanosecond. That means this clock equal to 0. This 0 will be retained for 5 nanosecond. Okay, after 5 nanosecond, clock is going to change to the value 1. Okay, so here after 5 nanosecond clock will be is going to change its value or logic from 0 to 1, and then again we are going to wait for 10 nano 5 nanosecond, clock period divided by 2, that means 5 nanosecond. Okay, so there you can change clock value also. Now we have considered in this program it is a 10 nanosecond, but you can change it to different values. That is, suppose you can take it as a 20 nanosecond, 50 nanosecond or 100, whatever you require. जी काही तुमची क्लॉक अवेलेबल असणार आहे त्याच्याप्रमाणे तुम्ही ती चेंज करू शकता. फक्त याच्यावरून या प्रोसेसमुळे काय होणार आहे की तुमचं क्लॉक हे क्लॉक पिरियड डिवायडेड बाय 2 एवढ्या टाइम पिरियड साठी ते 0 लॉजिक लेवलला असेल आणि उरलेल्या क्लॉक पिरियड डिवायडेड बाय 2 एवढ्या टाइम पिरियड साठी ते 1 लॉजिक लेवल असेल. म्हणजेच आपण इथे काय करतोय, क्लॉक डिफाईन करून घेतोय की तो किती वेळ असेल. आता इथे परत तुम्ही चेंज पण करू शकता की म्हणजे 50 here duty cycle for this clock is a 50%, but that also you can change depending on requirement. Okay, so now we have this as a 0 and 1 for each logic level will remain for 5 nanosecond. Now after that we are going to write a stimulus process. Okay, so this initially as we are keeping reset that is equal to 1. Okay, and then we are going to wait for 50 nanosecond. That means now your flip flop will be resetted. We are going to hold that value for 50 nanosecond. Okay, once we check for this time period, so whether we are getting correct result or not, after that we are going to change this values. Okay, now we are making reset equal to 0. Okay, now whenever our reset is equal to 1, that time output D out that is going to be as a 0 value. Now whenever reset is equal to 0, so whatever is input at D in, that will be available at D out. So now D in is equal to 0, so output will be D out will be equal to 0. Now again we are going to wait for 50 nanosecond, and after that we are going to make reset equal to 0, keeping reset equal to 0 again, but now we are changing D in that is equal to 1. Okay, then wait. Okay, so now we have checked all the test signal test vectors, because we have the inputs that is a reset and D in. So 0 0 combination as well as 0 1 combination that we have checked, and for reset equal to 1 that is also we have checked. So end of the process and then end of this architecture. So here once you simulate this program, so you will get the result like this. Okay, so initially what we have done, we have kept this D in that is 0. Okay, then reset that we have made as a 1. Okay, so for 50 nanosecond we have made reset equal to 1, and now if the reset is equal to 1, that means we are getting D out that is equal to 0. So D out will be at a 0 logic level. Again, this is the initial condition. After that we are again what we are doing, we are making reset equal to 0 and D in that is also equal to 0. So now with what will happen now? in this case we will get D out that is also equal to 0. So it will remain in the same state which was in a earlier case. So though reset is equal to 0, but as D in is equal to 0, so it will remain as it is. But now if reset is equal to 0 and we change D in that is equal to 0, so whenever clock is changing its value from 0 to 1, because we have considered as a rising age of the clock. So at the rising age of this clock, here you can see output is going to change its logic level from 0 to 1. So the first clock rising age of the clock, at that point your output will change from 0 to 1. Okay, so you can see though the input has been changed at this point, okay, but it will wait till the rising age of the clock. Okay, the output लगेच नाही चेंज होणार. जरी तुमचं इनपुट आधी चेंज झालं असेल, म्हणजे जरी इथं जरी चेंज झालं असेल या कंडिशनला, तरी पण जोपर्यंत तुमच्या क्लॉक सिग्नल हा राईज होत नाहीये, म्हणजे रायझिंग एज येत नाहीये, तोपर्यंत आउटपुट काय होणार नाही, चेंज होणार नाही. सो यू विल नॉट गेट देअर चेंज in the output. So you can see that here output is remaining as a 0, but whenever clock is changing its logic level from 0 to high, that time output will change from 0 to 1. Okay, and so you will get this type of result. Now this will remain till D out, D in has the 0 value. Now if D in changes to 0, again whenever D in changes to 0 at the rising age of the clock, D out will change its logic level. Okay, so it will change from 1 to 0. So this is about the output waveform for this D flip flop. Okay, so this is the about test bench for different circuitry. So similarly we can write test bench for another circuitry. So though this flip flop test bench was not there in the syllabus, but I wanted to show this simulation here. So that is why I included it in this part. Okay. So any doubt about this? Anyone has doubt? Okay, so
No
that
doubt, ma'am.
means whatever is going, you are understanding very well. Okay, so that's very good. This is about overall fifth unit actually. We have still finished fourth unit. So, but we are going to take that afterwards. Okay, so now we have completed our fifth unit. If you have any doubt, you can ask. Okay, we have still some time in today's lecture, or otherwise you can uh, call me or you can text me. So if you have any doubt regarding this topic. Okay, in the next session we are going to start with the sixth unit. So if you have doubt, you can ask. Okay, one more thing I wanted to ask, how many of you are having laptops in your class? How many of you are watching all these lectures on a laptop or PC? Shall I consider it as a no one is having laptop? Yes?